I'm not trying to make fun of the characters, the Looney Tunes. Okay, I am trying to make fun of people that deny that the moon landing ever happened. Okay, but anyway, one of the things that I saw on some hysterical post about how the government deceived us, and it was that, well, if they did land on the moon, why doesn't the Hubble take a picture of those landing stages? Because they're there, right? And these people no doubt have taken their home telescopes and tried to find them because they're big. They're 9.4 meters wide. It would take up most of the classroom area that I teach in, right? So why can't we see it, right? And the reason, the answer is that it's really far away, and the Hubble isn't all that big, right? Okay. So the question is, can you resolve this size object, right, using the Hubble telescope? Well, this will tell you what the Hubble can resolve, right? So let's find out what the Hubble can resolve. The Hubble can resolve. Let's figure out that angle. Well, that angle is going to be, we're going to use visible light because it's a visible light instrument, right? We're going to use its aperture, right? And so its resolving ability in radians is 1.22 times 550 nanometers divided by, and that's nanometers times 10 to the minus ninth meters, right? Okay, divided by 0.305. Okay, so this is, I'm going to go 1.22 times 550 e minus 9 divided by 0.305, and that angle that it can resolve is a neat and tidy 2.2 times 10 to the minus 6th radians. Okay? All right, now the Hubble would need to be able to resolve let's figure it out. Okay, would need to be able to resolve. Well, again, whenever you're figuring out an angle like that, right? It's like, imagine those are straight lines, right? This is L, how far it is away. S is how big it is, right? Okay, that angle is just as simple as S over L. Okay, how big the object is divided by how far away it is. Okay. So for this object, right, the angle we would need to be able to resolve is 9.4 meters at a distance of 384.4 times 10 to the 6th meters. Okay, that's not looking good, right? Okay, so let's look at this. 9.4 divided by 384.4 E6. And this is 2.4 times 10 to the minus 8th radians. Now, this is bigger than this. This is as small as we can resolve. This is almost 100 times smaller than that. So no, you wouldn't be able to tell whether it was a rock or whatever. It would just be the fuzz. It would be the pixels. It's like when you zoom in on a picture, a painting, right? A low resolution picture, you start to see the pixels, and God knows whether that dark pixel is a lander or a rock on the surface. You would not be able to resolve that. Okay, so then the question is, what size object could it resolve on the moon, right? And so if we take this angle and project it all the way out to the moon, right, that's going to equal some distance on the moon that we can resolve divided by 384.4 times 10 to the 6th. Those are megameters, by the way. So basically just take the distance to the moon, multiply it by that. So 384.4 E6 times the resolution of the Hubble, which is 2.2 times 10 to the minus 6th radians, right? And I get that the distance it can resolve on the moon is 845.68 meters. Now, mind you, that would just be the barest pixel. You'd be able to say, oh yeah, right? If you had two dark spots on the moon that were that far apart, you could say, oh look, that's two dots. You could just barely tell that that was two different things as opposed to one thing. That's what the Rayleigh criterion is, okay? Just keep that in mind, right? Hubble is good, but it's not that good.